section R2.8 on linear regression and models and R-squared. Okay, so the first example, we've got a table here that shows the number of multiple organ transplants in various years. T is the year since 2000. My first step is going to be using my calculator to create a scattergram of the data. And the key before I can actually start that is working with years. I have a starting year, and my starting year is since 2000. So I'm going to first make a table of T values off to the side. And since 2000, I've got 1, 2, 3, 4, 5, and 6. So in my calculator, I'm going to using the T values and then the N values. So the first column and then this last column over here for my two values. So in my calculator, I'm going to first go into the stat menu, then over to, edit, stat menu again. Number 1 is edit, so I can hit edit. Then if you already have data in from something previous, if you go up to where the list is, you can hit clear and enter. Note that you don't want to hit delete, that would remove the list, just want to clear it. Okay, and then type in your data. So 1, enter, 2, enter, 3, etc. And then go over to list 2 and type in those Y values. Oops, I typed that one in wrong. 338, 360, etc. All right, once you have them in, double check that your lists are the same length. Now the question is going to ask me to create a scattergram. Once the data is in the stat menu, we're going to go to y equals. If we have any equations in there, we'll clear them, and we're going to turn our plot 1 on. By default, the stat plot should already be set up, but if not, you're going to go into second, y equals, do stat plot, and just look at what plot 1 is doing. Right now, the type is dots, which is what we want for a scattergram, and the two things that it's graphing are list 1 and list 2. So back into stat, remember I put my data in list 1 and list 2, so that's what it's going to be graphing, so that's appropriate. So in y equals, my plot is on, and then I want to graph. If I just hit graph right here, I don't think anything is going to show up because the window would be a 10 to 10 window, and these are very much too large. Instead, I'm going to hit zoom. Option 9 down here is zoom stat. It is in the stat window, so I'm going to zoom in on stat. And then I can see my data. All right, now that doesn't look very good, so I bet I typed something in wrong. Those two are too low. I didn't look very carefully at those, but I bet I typed them in without enough digits. Oh yeah, so that was supposed to be 338. I went too fast on that one. That was supposed to be 448. I went too fast on that one. All right, that 338. I just typed real slow and I have repeated digits. There we go. Now, if I go back to my zoom stat or my graph, there, my data's looking a lot better. I'm going to do another zoom stat. Okay, so one way to correct errors is to check your window. All right, now that we see the data right here, back to our question. It says create a scattergram, include a sketch with a rough scale. All right, so my data looked like, so roughly like that. You can see that I had a lower dip and then a higher dip up there, so that's kind of a rough sketch right here. Now it also says a rough scale, which I can get from my window. I got my window automatically set up through my zoom stat. So I have, that's about 0.5 will be right there, and then this is about 6.5 is the end of the window, so if I just extend this a little bit further, it'll be about 7. Now, I have to be careful on my y-axis in particular because this minimum right here is not 0. It's 190. And then the maximum will be 618. Okay, so it's important to note that it's not 0 down here on this axis. This one technically wasn't either. It was 0.5. That's so close to 0 that I can say 0.5 would have been right there, and I can just scoop my axes over a little bit because I'm just sketching right here. Okay, now I'm going to answer some questions based off of my graph and my scattergram. So considering the scattergram, does a linear model appear to be appropriate? So it does. Why? Because if I imagine a line, I can imagine a line that's going to be close to the data. You want to be able to see something that one's not perfect, but something that's kind of in the middle where there are some points below and some points above. That one's probably a little high, but I just kind of drew a line right there. So yes. And then reasons are that the data has a general upward trend, so it's got a slope. So data is increasing, and it's roughly linear. Okay. You could also say out in words that a line will come close to most of your points. Okay. Explain why linear regression would be the best way to find that line. Okay, so we already said a line was going to be best. Why regression? That's because these points are not exactly linear, they are approximately linear. So the data is approximately linear. Abbreviated approximately, they're approximately linear. If I was to not use regression but write the model by hand, I would use 2 points and try to write the line myself. That would ignore the effects of all the rest of the points. Linear regression is going to use all of the points, find the center, the average of all the slopes, find the center of those points. The data is approximately linear, and regression will use all the points. All right. So this one can't be done by hand because it's not exactly linear. Now find the regression model. Okay, so I'm back onto my calculator. I'm going to hit the stat window. The first step is always to edit. I've already done that. Now I'm going to go to calculate, so the over arrow to calculate, and I'm going to choose my regression type. I want linear here, LIN, short for linear, number 4, linear regression. So I'll pick number 4. And then my data, remember, it was in list 1 and list 2. Those are there by default. That's what I'm going to keep it as. And I'm going to just go down from there to calculate. We'll talk about store a regression equation in a minute. Frequency list we don't use in algebra. They do use that in statistics. So down to calculate. And I have my linear model, so the form y equals ax plus b. I have an a value and a b value. And I also have these R-squared values below. I'll talk about those in a minute. First, let's write down our model. Okay. So find a linear regression model. First, I'm going to write the equation. The equation is y equals, the a value was 64.71. It said 2 places. X plus 188, just to confirm. Those were the values that I had for a and for b. Next, that's the equation, so I'll make a note of that. Technically, I was asked for the model, and so the model usually uses the variables of the problem. So I'm going to rewrite this one more time. Looking back up here, I can see that I was specifically told to use T for the number of years. I wasn't specifically told what letter to use the number of multiple organ transplants, so I can pick one, but let's say we use N for the number of organ transplants. So the model now would be N equals 64.71 T plus the 188. So the difference between our equation and our model is that it's going to use, the model is going to use the variables requested by the question. They're going to use the variables to make sense in context. N for number of transplants, T for years, T for time. Okay. All right, so some questions about our model. First, what's the slope of the model? I know it's linear. So in a linear equation, slope is the coefficient of x. You can see your slope value right there. So it is 64.71. The important bit is the what does it mean in this situation? I already know the number. I've got it from my regression. Okay. So it means that y values first, so the number of multiple organ transplants then what's it doing? That number is positive, so we'll say is increasing. And then by how much? By 64.71 transplants per what time unit? And again, the y unit is number of transplants, the x unit is years, so per year. Okay. So emphasize all of our pieces here, what it is, the number of multiple organ transplants, what's it doing? It's increasing, by how much and how often. Look at the back side of this page. Some more questions about the same one. Unfortunately, I have to flip back and forth a few times. The y-intercept, that was the b value. I remember that it was 188. And what does it mean? Remember that your y-intercept is technically an ordered pair, so it would be 0, 188. Technically, that's probably what I should have had in that line. And then in my interpretation, what it means, I'm going to need to talk about both of those values. So 0, that's time, is time since my starting year. My starting year was 2000, so we will say in 2000 there were 188 multiple organ transplants. Oops. that's the y-intercept. The t-intercept is one that I don't know yet, so we'll have to take the equation and solve it for t. So n equals, it was 64.71 t plus 188. If I want to find the t-intercept, we're going to set the equation equal to 0. And then solve for t. I know that I can first subtract the 188 from both sides. So that gives me negative 188 equals 64.71 t. Grab my calculator. I'm going to need to divide negative 188 by 64.71. Gives me a t value of negative 2.905. Okay. Now, t, time, was years since 2000. So if I add my starting year 2000 to that, what year would that put you in? Okay, you can literally just add it. So if you add on 2000, since it was 2.9, you're taking off a little more than 2 years, 2.9 years. You're really in the year 1997. 0.09. So it's actually early in the year 1997. So my year here is going to be that in 1997, there were 0 multiple organ transplants. And then I can go back up here and finish the intercept. I couldn't do that one immediately like I could the y-intercept. So I can go back up here, and the t value was negative 2.9, comma, the y value of 0. Depending on what you know about multiple organ transplant history, I don't know if 1997 was the 0th year or if there were other years prior to that that had them. It is possible this one could be model breakdown if we had some data to support the fact that there were multiple organ transplants before 1997. I'm going to leave it right now, but if you knew something about when the first one was, you might be able to declare if that was model breakdown or if it can stand. All right, part H. Use the model to predict the number of multiple organ transplants that will be performed in 2017. So 2017 is 17 years after 2000, so we're going to plug in 17. So n is going to be 64.71 times 17 plus 188. I'm going to grab my calculator and multiply that out. So we just have the 64.71 times 17 plus 188 comes out as 1,288.07. So we can conclude that in 2017 there were 1,288 multiple organ transplants. I think running to one decimal place makes sense here, but of course if it said keep 2, you would keep 2. Finally, part I, use the model to predict when there will be 1,000 multiple organ transplants. That's the n value. I want to set the equation equal to 1,000 and solve for the t value. I'm solving for t. We're going to subtract 188 from both sides, which will give us 1,000 minus 188, or 812, equals 64.71 t, and divide both sides by 64.71. 812 divided by 64.71 comes out as 12.55 for t, 12.548 or 55. Remember that that is the year value since 2000, so that's going to put us in 2012.55. You can argue whether that's 2012 or 2013. I say we're only halfway through 2012, so we will say in 2012. It was midway through, it wasn't there at the beginning of the year, but it was during that year. So there were 1,000 multiple organ transplants. All right, that finishes that example. It's a long one. If we're looking at the next page, we have some calculator directions. They're going to just remind us how to get to the stat menu, enter one edit to enter the data. Once you have your data in, how do you do the scattergram? So you're going to go to y equals, turn plot one on, and then you're going to the zoom key and zoom stat. If you need to set up the stat plot, what you're looking for is list 1 and list 2, and you want that dot. If it ever changes, you'll need to modify it back. Okay. And then on the back side, the directions for turning the diagnostics on and for doing a linear regression. I haven't mentioned the diagnostics yet, but I will. They are the R squared and the R value that showed up in my calculator. If yours are not on, one time only, you need to turn it on. If you go into your mode, you can go down to the bottom and there's stat diagnostics right there that you can turn on. You can also go into your catalog and look for diagnostic on. So if you go second 0 out of the catalog, go down to D's and do diagnostic on. Okay. Then the regression, we did this. So we did the stat menu, I already did the edit. So then we went into the stat calculate menu and we chose number 4 for linear regression. List, X list, Y list stayed the same. We wanted those at list 1, list 2, left blank, down to calculate. Okay, so keep the directions handy so that we know how to do our regressions. Okay. If you're interested, the next page has Excel directions. Sometimes in another class, you might be able to use Excel to do regressions as well. Okay. All right. Now we're going to look more on the next page, page 62, about determining the strength of models. That's where our R-squared value is going to come in handy. All right, so the R-squared value is called the coefficient of determination, and it's a measure of the strength of a relationship. R-squared is always under 1, or could be equal to 1. It's always in between 0 and 1, and it doesn't measure the direction, just the strength. And there's a couple rule of thumbs right here for gauging the strength. Okay, if R squared is equal to 1, the relationship is perfect, so it would be exactly linear. If it is bigger than 0.64, the relationship is strong. If it's between 0.25 and 0.64, it's a moderate relationship. Between 0.09 and 0.25, it's weak. If it's less than 0.09, there's no relation. Okay. Most of the ones that we're going to see in the class are going to fall into the strong category. We will occasionally deal with a moderate one as well. And there's just some pictures here to illustrate what those various things look like. Perfect positive, strong positive, weak positive. That one's no correlation. It doesn't look like a line at all. You can see your weak, really spaced out negative correlation, pretty strong negative correlation, and again, a perfect negative correlation. Okay. And then again, we could partition this. That's our perfect 0.64 to 0.7. That area would be the strong. 0.25 to 0.64, that's the moderate. Then anywhere from 0.09 probably over here, this is the weak. And then in this last range is none. So that whole middle bracket is the moderate. Strong and perfect are just at the right end right there, closest to 1. All right, so on the next page, we're going to look at some R-squared values. Then we're going to go back and get the R-squared value for the example that we've already done. Okay. So here we have 1, 2, 3, 4, 5, 6, 7 different graphs. We want to match them with their R-squared values. First of all, R squared being 1 is a perfect correlation. My dot should lie right on the line. So I would expect R squared to be 1 in part C, and I would expect R squared to be 1 in part F. They both look perfect, right? And it doesn't matter if it's a positive correlation or a negative correlation. Those are both perfect. Okay. Now, for the others, we have that one that's perfect. Then we have this 0.9 is strong. The 0.69 is also strong, but it's less strong, okay? The 0.35 is moderate. I'll just abbreviate that. The 0.19, that's going to be a weak. And then the 0.01 is going to be no correlation, just to put some names with each of those values. Let's see if we can figure out which of them is which. Okay. Now there are lines drawn through them. Those two are perfect, so I knew that they were going to be the ones. Okay. I would say, if I'm looking for strong, I would say that this is a pretty strong correlation. You can definitely see the shape of this line right here. So I want this one, I'll label it strong first. I want this one to be probably the 0.9. I think this one's also fairly strong, but it's less strong than this one. These are all grouped closer to the line. These are a little bit further away. So I believe that this one would be a good example for R squared 0.69. Okay. This one is pretty spaced out. I believe it would be weak. In which case, I think that its R squared value is the 0.19. It's also possible that it's moderate, although with those, if we took out some of these outliers, we might be able to say moderate. I think that one's going to be weak, and this one down here is going to be the no correlation. And so that's the one that's going to have the R squared value of 0.01. Okay. So just to get some ideas, it can be difficult to determine between two R squared values that are very, very close to each other, but they're far apart. You can definitely tell which ones are going to be in each of the categories. Okay. Besides the perfect relationships, which shows the strongest R squared, etc. So I think we've already done that. Okay. Flipping our page to the next side, consider the multiple organ transplant example again. Find the coefficient of determination. Okay. So if you don't already have your stat diagnostics on, you want to go down in your mode and turn them on. And then I'm going to go back to my regression, stat, calculate, number 4, linear regression, just recalculate it, because I didn't write down my R squared last time. Now I can see it. The R value doesn't mean anything to us right now, by the way, just the R squared. So I'm going to write down my R squared value, which is 0.9794 if I keep 4 places. 0.97938 or 0.9794. How strong is the relationship between these variables? Very strong. It's strong. There's not technically a very strong category, but I like to say it's very strong because that number is very close to 1. 0.97, can't get a whole lot closer. Okay, so those points were very close to the line. Okay, last example. As part of a larger study, we collected some ratings and nominations based on number characteristics from some fraternity men. And we said that, okay, men's romantic popularity correlated with several characteristics. That one got an R squared of 0.47. Best dressed, R squared of 0.48. Most attractive, 0.43, etc. I'm looking at my R squared values here, and we'll go back up and read those if we need to. So, which trait appeared to show the strongest relationship? If I want my relationship to be the strongest, I want highest R squared. So in this case, it's going to be the R squared of 0.48 because that's highest. So that would be best dressed. Notice that that's not actually a strong relationship. That's a moderate relationship. It's just that happened to be the strongest of these, right? So this is a moderate relationship, but it's the strongest of the ones listed. Because I had explained here, so it had the highest R squared. Okay. Which one was not significant? Not significant is going to be the one that falls into the no correlation, which is that bottom one. So men's potential for financial success, that's the one. Was not significant. because r squared equals 0.1 is less, well, it's actually really very close to the border of no relation, because the no relation border is 0.09. Okay, but we'll say because it is lowest. Okay, that is the end of R2.8.